Today we're going to be talking about Lab 3, the black hole orbit. Objective is to observe the motion of the star from the CSV file and use the information to determine the mass of the black hole. The result is that the black hole's mass is 3.5823 times 10 to the 31st kilogram. Note that unlike other labs where the object's position and motion was predicted using given condition, in this lab we are using the object's motion to identify the mass of the black hole. Some principles to know are the momentum principle. The momentum principle is the final momentum equals the initial momentum plus F net, which is the net force, times delta t. From that, we can derive that the net force is equal to the change in momentum or the change in time. And from that, we can derive that the net force in the parallel direction is equal to the dp dt in the parallel, and net force in the perpendicular direction is equal to dp dt perpendicular. Another principle to know is Newton's law of universal gravitation. We know this equation that the magnitude of the gravitational force is equal to the constant g times the masses of the star times the mass of the black hole divided by the distance squared. We will use this equation right here, the mass of the black hole, in our code later. This is derived from the mass of the black hole right here, which we rearranged some variables from the original equation and found. Now we'll go to the VPython code. Here is the code that I uploaded. First, I changed the mass of the star and added the gravitational constant. Also changed the delta t and the time, which is equal to 0, from initial conditions that I was given. I read the CSV file that I was also given. In this first while loop, all we're doing is computing the velocity in the x component and in the y component. In the second while loop, we are computing the initial and final velocity as well as the initial and final momentum. This is done by multiplying the star's mass times the velocity. We also found the change in velocity and the change in momentum. From this, we can find dp dt, which equals dp delta p over delta t. And from Newton's second law, we know that F net equals dp dt. To find F net in the parallel direction and F net in the perpendicular direction, we use some more coding and some calculus. For the F net in the parallel direction, we found p hat and the derivative of the magnitude of p divided by the change in time, and we used the momentum and time to figure this out. And we know that F net parallel is equal to dp dt parallel. dp dt perpendicular we found by subtracting from dp dt minus dp dt parallel. And also from Newton's second law, we know that F net perpendicular is equal to dp dt perpendicular. The arrow scale is used to show the arrows in the observation screen. This right here, black hole's mass, as we talked about earlier, will show me the black hole's mass from the computational model. It takes into account the net force, the relative position vector, and the constant g, as well as a star's mass. Here you can see that the last thing I'm printing is the black hole's mass. Next, let's run the code. As you can see, here is the orbit. The yellow arrow is the net force, the blue arrow is the perpendicular net force, and the parallel net force is in the black arrow. As you saw, the net force, which is the yellow again, always pointed towards the black hole. This is because the only force is the gravitational force. The blue arrow, which is the perpendicular net force, did not point to the center, it pointed to the center of the kissing circle, and since it's not a perfect circle, yet an ellipse, it did not point to the center. The black arrow told us about the speed, and as you can see in the beginning, it wasn't changing speed, but as it got closer or to the side of the black hole, it was changing speed and increasing speed. And as we said, the last print statement shows the mass of the black hole, which, as I said before, was 3.5823 times 10 to the 31st kilograms. Next, let's answer some what does it mean. In your analysis, you should discuss how the F net perpendicular, F net parallel, and F net are different from dp dt perpendicular, dp dt parallel, and dp dt. We've already stated the momentum principle and the gravitational force, and we'll use this to answer this question. It is different in the way that they are calculated. To find the net force in this case, you just use Newton's law of universal gravitation, and to find dp dt, you have to use some calculus by dividing the change in velocity or the change in time and then multiplying that by the mass. Another difference is that dp dt does not affect the star's motion, while Fnet does. dp dt just tells us how the star moves. Also, the net force can be found by adding up all the forces acting on an object, while dp dt is found by observing the motion of the object. Even though they are equal to each other by the momentum principle, they are found in different ways. Let's answer this what-if question. Imagine the black hole whose mass you found was removed, and a different black hole was placed in the same location. Assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. Could you tell the difference? So, we're making the assumption that the motion is unchanged so that the data points of the star, so that the location, the x and y, is going to be unchanged. Stating that the magnitude, relative position magnitude, will be unchanged. G is a constant, so it's unchanged. The star's mass is unchanged, and since the motion is unchanged, the magnitude of Fnet will be unchanged. So the black hole's mass should be the same. So we cannot tell the difference. Thank you. And this is the end of my video.